this video, I want to briefly revisit the concept of work. And we're going to talk about in later videos how work is applied to general planar motion. But for this, I just want to revisit the definition and kind of explore what that means a little bit. So recall that when we talk about energy, we can use a base equation which looks something like this. And in this base equation, we have kinetic energy and we have work. So what this means is that T1 is the kinetic energy in some state, state 1, and that means that a rigid body is moving with some motion that causes this kinetic energy. Could be translation or it could be rotation. T2 is the kinetic energy in this other state after something has happened. So two different states, 1 and 2, two different kinetic energies, two different states of motion. The term in the middle then, U1 to 2, is basically the work that is input to the system. So what are we doing to this rigid body that is causing this change between states 1 and 2? So we often can think of work in a couple of different terms, but from a mathematical standpoint, I'm going to say that work is equal to the integral of some force applied over some distance, and we're integrating over this change in position from P1 to P2. So this is the application of force over a distance. And we often see this, represented in terms of a variety of things, but if I push a box across the ground and push with a constant force, I would determine how much work I've done or how much energy I've put into that system in the form of work by multiplying the force that I apply times the distance over which the box moves. Same thing if I go up a set of stairs. The amount of work that I'm doing is equal to how much force I'm applying, probably my weight, and the distance I'm traveling up those stairs. When it comes to using this mathematical representation, the main thing that we have to take into account is that, well, the force doesn't necessarily have to be constant, right? I've written or used it in the past mainly as a constant, but it doesn't necessarily need to be, and we can integrate over changing force, especially if we know the force, how the force changes over this change in position. We can also write work in terms of rotation. So if I integrate over some change in angular position theta, I could integrate the moment that I'm inputting over that change in angular position. And I could think of this as a torque applied over a rotation. So if I apply a torque to something, I twist it, I apply a torque, maybe here with my fingers, and it twists or moves over some change in angle theta, I'm doing work on that system, right? I'm changing the state of what's going on. And just like in force, if m is constant, not changing over time, then the equation simplifies. So let's start up here. If F is constant, then U1 to 2 is F times P2 minus P1. And the same is true for moment. If M is constant, then we have the same expression. So in thinking about this, many of our problems, many of the things we might try to look at would involve these constant forces or constant torques. And as a result, we could use these, slightly simplified versions of the equation. And ultimately, we're looking for how this contributes, either in addition to the kinetic energy or in taking away from the kinetic energy. And in that way, we can balance the equation for energy that I have up on the left. All right, thanks.